Okay, in this class I'm going to go back over word problems with differential equations. I'm going to go back over an example we looked at previously. I'm going to solve it in a slightly different way. But before I do, just a couple of things about integration. One thing, if I have, I want to find the antiderivative of a function of this form, 1 over ax plus b, where a and b are constants. You know, if I want to solve this using a u substitution, I can let u equal to ax plus b. Take a derivative. This is called a u substitution. Take a derivative of u with respect to x. What we'll just get is a. B is a constant. Derivative of any constant 0. Derivative of any constant times x is just that constant. And then I'm going to actually solve for dx in terms of the other variables. So dividing on both sides by a, multiplying on both sides by dx. So what I can do here with an integral of this type is I can kind of reframe it as 1 over, well, we said ax plus b, we decided to call that u, and dx we said is going to be 1 over a du, so 1 over a is a constant, factor it out, times du. So what I get if I take the antiderivative there is 1 over a times the natural log of the absolute value of u, okay, plus c. Again, unsubstituting now this value for u back in, so we're going to get the natural log of the absolute value of ax plus b all over little a, the leading coefficient there, plus c. So it's the natural log of the denominator here divided by the leading coefficient of the denominator for antiderivatives of this type, 1 over a linear polynomial. It's just for 1 over a linear polynomial. That's what we're looking for. So if I have 1 over 20t plus 1, I'm taking the derivative with respect to t. What we will get is the natural log of the absolute value of 20t plus 1 all over the leading coefficient of 20t plus 1, which is 20, and plus c. Okay? And that's actually worth remembering, you know, that the antiderivative of 1 over ax plus b, where a and b are constants, with respect to x, is that thing there. That is not given in your formula and tables booklets, but has come up in past exams. So if you can learn that off, if you can't remember how to learn, if you can't remember it, just understand the u substitution. Fairly straightforward u substitution in this case. Okay, that's the first thing. The second bit of background information is just how we define these things. Remember, s is the change in position, v is the derivative of s with respect to t, or the derivative of x with respect to t, where x is position. A can be written as the second derivative of s with respect to t, or the first derivative of v with respect to t, or v dv ds. And I've gone up through all of those things in previous lessons. In this class, I'm going to look at solving a problem a bit like the one in fact, identical to the one I did in the last lesson, however, using a different substitution in order to solve it. So let's have a look. An object moves, so its deceleration is equal in magnitude to the square of its velocity. And again, this is an example I've gone through before. So we were able to say that a is equal to negative v squared. We were also able to say that v was equal to 20 when t was equal to 0 and s is equal to 0. And the question is, how far will it have traveled when its velocity is 10? Find s when v is equal to 10. Now the most efficient substitution to use here is v dv ds for a. However, I want to look at a different substitution. I want to look at using a different substitution here. So I'm going to use the substitution dv dt is equal to a. So that's the substitution I'm going to use. So a is equal to dv dt, so I can say dv dt is equal to negative v squared. Separate, dividing both sides by v squared, I'm going to get v to the power of negative 2 over here. Remember, it's 1 over v squared, which is v to the negative 2. Multiplying on both sides by dt, I'll get negative dt, and then I'm going to integrate, factoring out the negative 1. So that's going to be v to the power of negative 1 over negative 1, which we'll simplify in a moment. This will be negative t plus c. V to the power of negative 1 is 1 over v, so I'm going to get negative 1 over v is equal to negative t plus c. Okay, I want to look at the constant of integration here, so I'm going to go back and look at my initial conditions. We know that v is equal to 20 when t is equal to 0. So therefore my particular solution here, negative 1 over v, is going to equal to negative t. Sorry, I've just t is equal to 0, so negative and v is equal to 20. Okay, so negative 1 over 20, apologize, is equal to negative t, that's 0 plus c, which is just c. So we can establish that c is equal to negative 1 over 20, and then we can take it from here. I'm going to scroll down the page a little bit, because this is a slightly longer answer here. So I'm going to scroll down the page. So looking at my general solution here, or my particular solution I should say, therefore negative 1 over v is equal to negative t, and subtract 1 over 20. So I can solve for t here. T is going to equal to 1 over v minus 1 over 20. Okay, and I can also solve for v. Let's just solve for t at the moment, because I'm going to find the time at which the velocity is 10. We're trying to find ultimately the displacement when the velocity is 10, but first I'm going to find the time. So when velocity is 10, what do we get? Well, we get t is equal to 1/10, which is 2/20, minus 1/20. 2/20 minus 1/20 is 1/20. So one thing we're able to establish early in this case is that v is equal to 10 when t is equal to 1/20. So v is equal to 10 when v is equal to 1 over 20. Okay, I want to find s. So what I'm going to do is solve for s in terms of t and then substitute back in. And to do that, I'm going to go right back up here to my solution. 1 over v, negative 1 over v equals negative t minus 1/20. So my next stage is to say we know negative 1 over v is equal to negative t minus 1/20. Multiplying on both sides by a negative 1, we're going to get 1 over v is equal to t plus 1/20. And expressing t plus 1/20 as a single fraction, that's going to be 20t plus 1 over 20. T is equal to 20t over 20. So what I have is 1 over v is equal to 20t plus 1 over 20. The next thing I'm going to do is just take the reciprocal of each of those sides. If two fractions are equal, then their reciprocals are equal. So v over 1 has to equal to 20 over 20t plus 1. Okay. Remember that v is equal to ds dt, so I'm going to substitute in now. ds dt is equal to 20 over 20t plus 1. And now, I'm going to separate that, multiply on both sides by dt. So I'm going to get ds is equal to, I'm going to factor out the 20. It's going to be 20 times 1 over 20t plus 1. And I'm also multiplying by dt on both sides. And that's separated, and now I integrate. So on the left hand side, the antiderivative of 1 with respect to s is just s. Over here I get 20 times the antiderivative of 1 over 20t plus 1. What did we say that was? Well, actually we went through this just before we started this question. It's the natural log of, let me scroll down, it's the natural log of 20t plus 1. 1 over 20. And then plus the constant of integration. Notice the absolute value brackets here. Time is always positive, so 20 times time is always positive. 20 times time plus 1 is always positive. So actually I don't need to worry about absolute value brackets. The other things here is the 20s are cancelling, so we get s is equal to the natural log of 20t plus 1 plus c. But we know that s is equal to 0 when t is equal to 0. How do we know that? Well, that's always the case. Displacement is always 0 when the time is 0. Displacements change in position. If there's been no change in time, there can be no change in position. Substituting in here, I'm going to get 0 equals the natural log of 0 plus 1, which would be the natural log of 1 plus c. The natural log of 1 is, of course, 0, so we get c is equal to 0. Going back to my general solution here and plugging in 0 to find my particular solution, s can be written as the natural log of 20t plus 1. Okay. The question was find the displacement s when the velocity is 10. Well, we figured out halfway down here that the velocity was 10 when the time was 1 over 20. The time was 1 over 20. That's an error I've made in the question. Apologies. When the time was 1 over 20, v equals 10 when t equals 1 over 20. So I'm going to substitute in here. We're trying to find s when t equals 1 over 20. So when t equals 1 over 20, s is equal to the natural log of 20 times 1 over 20 plus 1. 20 times 1 over 20 is, of course, just 1. So we get the natural log of 1 plus 1, which is the natural log of 2. And that's the displacement. The units will be meters. And that's an alternative solution. Now, I'm hoping you've gone through the other video first, because it's a much more efficient and quick way to get there. However, the reason I'm going through this is to show that both substitutions in this case will actually work. In the second example, I've found the time where the velocity was 10, and then from that found an expression for displacement in terms of time, and substituted my value for time. In the first video, we just found a relation between s and v very quickly, and we were able to solve that much more efficient. Okay. However, this is an alternative solution, so both substitutions will work, which is really ultimately what I wanted to get across. Also, remember, learn this by heart. That's how we find the antiderivative of 1 over ax plus b. Okay, so practice, practice, practice.